Welcome to the second part of working with trig graphs. In today's video we'll look at horizontal transformations. Last time we recapped the intro video and then went on to use the unit circle to see where the graphs come from. We then plotted the trig graphs using the unit circle as a guide, then we used the graphs to talk about amplitude, which is just the height of the graphs, and highlight the two types of vertical transformations. We then looked at the general form of these trig equations, allowing us to look at the transformations in more detail. And using Desmos, a graphing calculator, we explored vertically stretching and compressing the graph, and then we also looked at vertical shifts. And we finished with looking at some physical applications of what we've done, and mentioned that we'll do some more detailed examples and past paper questions in the examples video to follow this one. I recommend having a look at part 1 first, the link will be in the description, but for now, let's get started with horizontal transformations. Just like there's a vertical shift, there's also a horizontal, or phase shift. Let's sketch a horizontal shift of 45 degrees to the right. So we start at 45 and we go all the way around, but we have to stop at 360 because we only sketch between 0 and 360. Which means in order to finish the curve, we need to go back from where we started, back to the axis. But where does this extra part of the graph come from? We're running a similar problem when we consider a horizontal compression, so let's compress it by 2. So it's now half the size it used to be. But as we can see, we've not got a full graph between 0 and 360. So in order to get a full graph between 0 and 360, we need to do another full curve. And these are the correct ways to sketch these two types of transformations. But in order to better visualise where these extra parts of the graph are coming from and how exactly it all works, we're better off thinking about what happens to the graphs outside of 0 to 360, even though we only sketch what happens inside 0 to 360. I'll show you what I mean. So here we have the regular sine and cosine graphs, but what we've sketched here is actually the parts of the graph between 0 and 360. The curves actually extend beyond this, both in the positive direction and in the negative direction, to positive and negative infinity. And both the sine and cosine graphs do this. And when we sketch out the full graph, or as much as we can show on the screen, you can see that they're both the exact same shape, just offset by what's called a phase, a horizontal shift. And both these are what's called a sinusoidal shape. The reason we only sketch between 0 and 360 is because if you just look in this region, you can see that both the graphs just repeat themselves after they leave this region. And that's because one way to find the graphs is from the unit circle we talked about last time. A circle's only got 360 degrees, so it just repeats itself after it goes round once. And this means we can say that both graphs have a period of 360 degrees, and the period is just how long it takes the graph to complete one full cycle. While we're talking about the period of graphs, I also want to mention tan briefly. So just like sine and cos, tan also extends in both directions infinitely. It's a little bit more strange shape, but it does the same behaviour. But what you might notice is if we draw a line at 180, it actually repeats itself after that 180. And this means that tan only has a period of 180 degrees, which is half of that of sine and cos. So back to our graphs here. Let's see how this picture can help us understand horizontal transformations a little bit more. So let's look first at our compression. So let's compress it by 2. And we can see that there's now 2 waves in between 0 and 360, and that comes from taking the whole graph and squeezing it until you've got the right amount of graphs in the waves between 0 and 360. And we can also stretch it by 2. And we stretch it out until it's twice as long, and we can see that now it has half a wave between 0 and 360. And we'll do the same for a shift, so let's shift it right by 45 degrees. And we see this corresponds to taking the whole wave and moving it 45 degrees through. And this is how we get the shape that we had before between 0 and 360. And we'll do the same for a shift to the left by 45 degrees. And you can see that this gives us a bit more of an intuitive picture about how we actually end up the graphs that we do by looking at the whole graph and not just between 0 and 360. Recalling the general form of the trig equations, we can now see what the blue B is about, because last time we looked at how the amplitude, the red A was the amplitude, and it corresponds to a vertical stretch or compression. This time we'll look at how the B represents how many waves there are between 0 and 360, and it corresponds to a horizontal stretch or compression. And last time we looked at how the C in the end, the plus C, represents a vertical shift by moving the graph up or down. You'll notice that the horizontal translation, the horizontal shift, isn't here, and that's because that one takes a slightly different form that we'll look at later on. Recalling the transformed graphs from before, we can see that the horizontally shifted graphs still only have one wave between 0 and 360. Ignore this squiggly line. They might all start at different points, but they all get one complete cycle in between 0 and 360, and this is because the number b in front of them is all unchanged. There's no number in front, they're all just ones in front of all the x's, which means that the number of cycles between 0 and 360 is still 1, and the period remains the same, 360 degrees. Whereas for the ones on the right hand side, we can see that b is different for them. For sine 2x, there's now 2 waves between 0 and 360, the yellow one, between 0 and 360. Whereas for the 0.51, there's only half a wave between 0 and 360. And this means that the period is also changed. So for sine 2x, there's 2 waves between 0 and 360, which means it repeats every 180 degrees. So just after here, it repeats itself, which means its period is now 180 degrees. And the y equals sine half x will now have a period of 720 degrees before it repeats itself. Let's summarise this. So the blue b, the number in front of the x, is how many waves there are between 0 and 360. And it affects the period but is not equal to the period. So for example, when b is larger than 1, we notice this resulted in a compression, so we have 2 waves between 0 and 360. Notice this is opposite to the vertical one, where bigger b meant stretch. If b is less than 1, then it's a stretch, and we have half a wave. For example, for 0.5, we have half a wave between 0 and 360. And in general, the period is how long it takes to complete a full cycle of the wave. And in order to figure out what it is, we just take 360 and divide it by b. So for example, for the white one, b is 2, so the wave repeats every 180 degrees. And when the b is 0.5, when there's half a wave between 0 and 360, the period becomes 720 degrees, because that's how long it takes to complete a full cycle. So I've now covered how all 3 letters in the general trig equations affect the graphs. But there's one more, the horizontal shift, that we've not covered, and this is because it takes a slightly different form. It looks like this, where we have a number, d, add or take away, depending if it's positive or negative, from the x inside the bracket. And we could add this in the general one and get a bigger general one that includes all 4. This is perfectly fine, but looks a bit messy and it's quite a lot going on. In practice, in your exams, etc., you only ever see a combination of maybe 2 or maximum 3 layers. For example, here you can see that only the A and the D is present, and in this example here, only B and C are present. So this is this little diagram that highlights how all 4 of them affect it in the big general equation that I've made. But again, you won't have all 4 in one question. You'll have 2, maybe 3 max. So we'll move on from this. Let's look at the horizontal phase shift in a bit more detail. So we can see for the dark blue one, when D is positive, i.e. we've added on 45 degrees, this results in the graph going left, which is actually opposite to how you might think it would work. If it's positive, usually that's about going right, but just like the horizontal stretch or compression, you actually work out and do the opposite way to what your intuition tells you. And we can see the same for here, where D is negative, we actually go right instead. I will leave a link in the description so you can use the Desmos graphing calculator to have a look at both the horizontal phase shift as well as the horizontal compression / stretch, just like we did in the first video. Now let's summarise what we just found. D is just the amount that's been shifted left or right. And if D is negative, instead of going left like our intuition might tell us, we go right instead. So for example, if D is 45 degrees, then we start 45 degrees away from the axis and we draw until we get to 360. And then in order to get a full wave between 0 and 360, we extend it back towards the axis. And that's us imagining that the whole graph is pulled in, and this is just what it would look like before 0. It's been pulled in to be between 0 and 360 now. And if D is positive, instead of going right, which is usually what we associate with the positive direction, we go left. And so for example, if D is negative 45, then we'll start off at negative 45, which is roughly where that is in the axis. And we'll draw out the full sine curve, and then we'll rub it that little bit before 0 because that's not actually between 0 and 360, and we'll extend the sine curve at the end until it gets 360. And I found this is the best way to draw accurately the horizontal phase shift transformations. And it is the hardest one to draw, so don't get too stressed if you're not finding it very easy. Now that's us covered all 4 types of transformations in depth. I just want to highlight a few things before we end. If the letters are outside of the function, i.e. before the sign or cos and after the bracket, then that means they correspond to some sort of vertical transformation. And for the vertical transformations, they perform as you would expect. And what I mean by that is, for positive c, we just go up, for negative c, we go down, and for a bigger than 1, it's a stretch, and for a smaller than 1, it's a compression, and that kind of lines up with intuition. Whereas if the letters are inside the function, inside the square brackets I've drawn here, then that means it corresponds to horizontal transformation. And as we've discussed, these kind of go opposite to what we'd expect. I.e., if d is positive, we go left instead. If d is negative, we go right. And if b is bigger than 1, it's now a compression, because that's how many waves that you fit between 0 and 360. So if it's 2, we need to fit 2 waves, so we have to compress the graph in. And if b is less than 1, then it corresponds to a stretch. In the examples video to follow, we'll do 2 sketch given equations and 2 equations given the sketches. And now let's round out the video with why we care about these vertical transformations. The different values of b and sine bx actually make up the different harmonics in music. So for example, this top one here would be sine 0.5x, because there's half a wave between the start and finish, between here and here. The next one down would be just regular old sine x, because there's only one wave between the start and finish. And so on. The next one would be sine of 1.5x, or 3 halves, because there's 3.5 waves between the start and finish, and it goes on in increments of a half after that. We spoke in the intro video about Fourier series, and these series are made by combining sine and cos waves of different b values. And this number here is just how many of these different sine and cos waves are combining, and we see we can make any arbitrary function we want. So this is making some obscure triangle and square wave function. And if we expand this to 2D, we can see we can make much more interesting pictures like this phoenix here. And if we write the trigonometric functions in terms of time, t, instead of x, then b is just the frequency. And the frequency determines the curl of light and the type of electromagnetic wave in general. Frequency also determines the pitch of sound waves, which is the notes we hear. That brings us to the end of today's video. I hope to see you in the following examples video.